quantum relativity and multiverse. When you take Einstein's general theory of relativity, the modern theory of gravity, it gives us our understanding of the Big Bang and all of modern cosmology. Then comes quantum physics, which emerged about 10 years later, in the 1920s. That's the science of molecules, atoms, nuclei, and subatomic particles. But here's the kicker. These two theories, relativity and quantum mechanics, do not play nicely together. Each works beautifully in its own domain, but try to combine them and it all falls apart. They're fundamentally inconsistent. So, what happens at the very beginning of the universe when everything was compressed to the size of an atom? Whose rules apply? That's the shotgun wedding general relativity and quantum physics forced into union. And most physicists agree, quantum physics likely wins in that scenario. Why? Because quantum mechanics allows particles to pop in and out of existence. And if the entire universe was once the size of a particle, it's possible that universes themselves could pop in and out of existence. That means multiple universes could be bubbling into reality all the time. Ours is just one of them. Each could have slightly different laws of physics. If there are infinite universes, then every possible combination of particles must exist, including a version of you with an evil mustache. Or an evil goatee, or I don't know, a nice version of you living their best life in some parallel universe. But here's the thing, even if another you exists, there's no reason to believe your consciousness overlaps with theirs. You don't share consciousness with your identical twin in this universe, someone made from the same cell as you, so why would you with a copy of yourself in another universe? And that leads to another mind-bender. Asking what was around before the Big Bang is like asking what's north of the North Pole. The question itself has no meaning. The singularity happens. Boom! Then time, space, everything we know, all of it is contained within that point. But if space is nothing, what does it even mean for it to be inside something? Your head starts to hurt trying to think about it. You need a new word to describe a place where space doesn't exist. We should call that something, because nothing isn't really nothing. It's something. Now picture this. The singularity is embedded in a higher dimension. Imagine an ant crawling on a piece of paper. That paper is its entire universe. It has no concept of what's above or below the paper, but we do. We can lift it, fold it, see underneath it, but the ant can never experience that extra dimension. In the same way that nothing surrounding the singularity might actually be a something in a higher dimensional space. Life as we know it is made from what we call organic elements, carbon, oxygen, nitrogen. But those didn't come from the Big Bang. They were forged in the hearts of massive stars and then released into space when those stars exploded. You need generations of stars going supernova to build up those elements. Later gas clouds gather that enriched material, and from that, new stars and planets form, ones that can support life. That's why, when looking at very old stars, it's unlikely you'll find planets with life. But fast forward 5 billion years, the universe might be teeming with life because there'll be so much more organic material available. Some planets might even have multiple origins of life. They could be tripping over life, so much material, so many chances. Now why is everything in the universe round or curved? I wrote an essay called On Being Round. The laws of physics conspire to make things round, even when you might want them some other shape. Planets, stars, bubbles, roundness dominates. You can just Google Neil deGrasse Tyson on being round, and make sure it's not Mike Tyson unless you want a book called On Being on the Ground, where he knocks you out. And finally, weather. We use simulations to predict it. These are called climate models. They work because we test them on past data, real stuff that's already happened. If the model doesn't work, we go back, refine it, and improve it. So when they say 50% chance of rain, that's just what the best version of the model can predict with current data. In the future, we'll want models accurate enough to give us near 100% certainty. We're not there yet, but we're getting better all the time.